Hello one and all. Let us discuss about sampling of continuous time signals, analog signals. Its basics. The basic concepts of sampling process will be explained in this video. Sampling is the process of conversion of a continuous time signal into its equivalent discrete time signal. The sampling is performed by taking samples from a continuous time signal defined at finite intervals of time. Time interval between two successive samples is called as sampling interval, and it will be uniform and it will be the same. Such type of sampling is called periodic or uniform sampling. Periodic or uniform sampling. So x of t continuous time signals will be the input. The process will be sampling, output will be discrete time sequences. Sampling process is modeled by a switch which is closed in once in a finite interval of time, so that x of t will be converted into its equivalent x of n dt sequences. So Fs, sampling frequency. Inverse of sampling period is called a sampling frequency or sampling rate. Sampling rate will be indicated by hertz or cycles per sample. The time interval between successive samples is called as sampling time. Sampling interval, it is denoted by Ts or T. Unit of sampling period is capital T, seconds. It may be milliseconds, or it may be microseconds, or it may be seconds. Inverse of sampling period is called sampling frequency or sampling rate, Fs. Unit of sampling frequency will be maybe hertz, kilohertz or megahertz. Rate of sampling. When an analog signal, continuous time signal, is applied as an input, xa of t or xi of t, is applied as an input to a switch which is closed once in a time interval nts, where n is an integer. N may be equal to 0, n may be equal to 1, or n may be equal to 2, or n may be equal to 3. 1 ts, 2 ts, 3 ts, 4 ts, 5 ts. Once in every ts duration, the switch is closed and the sample is passed to the next side, so that discrete time sequence is generated. X of nts, which is equivalently represented as a sequence of samples taken at once in ts duration, recorded as sequence of samples. So it may be x of n, which is equal to some samples, x of 0, x of 1, x of 2, the magnitude of the signal at integer sampling intervals. So let us see. Xa of t is an analog signal or a continuous time signal. X of n is a discrete time sequence. Generating discrete time sequences from an analog signal is called sampling. So xa of t, in which we are replacing t is equal to n into ts. T is replaced by nts, so that the sample will become x of nts. Ts is equal to 1 by fs, or it is equivalently represented as x of n. N is in the range of minus infinity to plus infinity, but please keep one thing in your mind, it will be of only integer values. Ts or t is called a sampling period or interval in sampling interval in seconds or milliseconds or microseconds. Fs is called a sampling rate or sampling frequency. It will be denoted with units hertz, kilohertz or megahertz. Let us see how an analog signal is sampled. Xa of t, a cos omega naught t plus theta, is a general continuous time signal. Omega naught is replaced by 2 pi f naught. 2 pi f naught into t plus theta. We all know that f naught is called analog frequency which is actually obtained from omega naught divided by 2 pi. Frequency of analog signals in terms of hertz or kilohertz or megahertz. XA of t is sampled at intervals of t or t seconds to generate a sequence of samples. Now, let us see. T is replaced by n into Ts. Omega naught n Ts. Omega naught is replaced by 2 pi f naught. And Ts is replaced by 1 by Fs. So 2 pi f naught 1 by Fs into n plus theta. Let us assume that f naught by Fs is equal to small f. Discrete time signal frequency. See the difference. Capital F naught is the analog signal frequency, small f naught is its equivalent discrete time signal frequency. Now it is represented in short form as 2 pi f naught by 2 pi f naught into n plus theta. As you all know, 2 pi f naught will be represented by omega naught. Omega naught. So I just mention things in, see, a cos omega naught t plus theta now becomes a cos omega naught n plus theta because of sampling, where f naught is equal to capital F by Fs is called frequency of discrete time sinusoid sequences. Cycles per sample is the unit. And whenever you get a term 2 pi f naught, you have all rights to replace it with omega naught, angular frequency of discrete time sinusoid, radians per sample. Capital F or f naught is called analog frequency, whereas small f is called a discrete time frequency. Continuous time frequency is capital F and discrete time frequency is small f. The range of capital F will be minus infinity to plus infinity. The range of small f is minus 1 by 2 to plus 1 by 2. So sampling of analog signals, infinite frequency range of continuous time signals are mapped to finite range of signals, finite range of frequencies in discrete time domain. Range of analog frequency is minus infinity to plus infinity. Range of small f will be minus 1 by 2 to plus 1 by 2. So infinite range of frequency signals are mapped into finite range frequency signals in discrete time domain. It's an important key result of sampling. You view it as if signals are, you viewed it as if the signal is sampled and samples are generated. It's a sampling process. But most importantly, what should you remember? Range of minus infinity to plus infinity frequencies are going to be mapped into minus 1 by 2 to plus 1 by 2. Okay? So let us see. Since small f discrete time frequency is equal to capital F by Fs, small f is in the range of minus 1 by 2 to plus 1 by 2. That means small capital F divided by Fs is equal to, is a range between minus 1 by 2 to plus 1 by 2. Right? Good. Similarly, if I adjust this inequality such that it is like taking capital F is a set of values between minus Fs by 2 to plus Fs by 2. The highest analog frequency that can be uniquely represented by discrete time sequences Fs by 2. Did you notice? It's an important process or the result consequence of sampling to be remembered. Highest analog frequency that can be uniquely represented by a discrete time sequence will be Fs by 2. Continuous time signal with frequencies above Fs by 2, what will happen? They will be represented as another signal within the range minus Fs by 2 to plus Fs by 2. That is one of the issues, you should always limit, because you cannot go beyond fs by 2. If any signal fs by 2 greater than fs by 2 is present, when it is reconstructed, it will be reconstructed as a signal, one of the signals present within the same range of minus fs by 2 to plus fs by 2. Continuous time signal with frequencies above fs by 2 will be represented as a signal within the range minus plus fs by 2 to minus fs by 2. Hence, the signal with frequencies above fs by 2 will have an identical signal with frequency. Signal with frequencies greater than fs by 2 will have an identical signal with frequencies below fs by 2 in the discrete time domain, seemingly taking an identity. So, infinite number of high frequency continuous time signals will be represented as a single discrete time signal. Such signals are called in the name of allays. Such signals are called in the name of allays. Infinite number of high frequency continuous time signals will be represented by a single discrete time signal. Such signals are called as allays. While sampling at a frequency of fs, make sure that the frequencies above fs by 2 will have an allays with frequencies below fs by 2. So it is called as point of reflection. The point of reflection is folding frequencies fs by 2. Folding frequencies fs by 2. Point of reflection. So please ensure that before sampling, when you are sampling at a frequency fs, see to that your input signal does not have any frequencies greater than fs by 2, so that samples are generated properly. While reconstructing them, automatically it will be perfectly reconstructed. The condition is revealed. Clear? And one more point I just want to mention. If the sampling frequency is any multiple of, I'll repeat, if the sampling frequency is any multiple of f1 minus f2, any multiple of f1 minus f2, f2 will be an allays of f1. That is an important point to be kept in mind. Any multiple, k may be equal to 1, k may be equal to 2, k may be equal to 3, k may be equal to 4. When there are two components in the composite signal, first of all, you must look into the maximum frequency, and you have to set a sampling frequency twice that of the maximum frequency. That is condition number 1. And see to that if you select a sampling frequency such that it will be any multiple of, any integer multiple of f1 minus f2, unknowingly if you have selected that as fs for sampling the signal, f2 will be an allays of f1. This phenomenon of high frequency component taking an identity, getting an identity of low frequency component because of sampling with wrong sampling frequency is called in the name of aliasing. I'll repeat, the phenomenon of high frequency component seemingly taking an identity into low frequency component because of sampling, wrong sampling frequency selection during sampling process will be called in the name of aliasing. Say, I should first of all look into the maximum frequency of analog signal that can be uniquely represented as a continuous time signal, as a discrete time signal when sampled at a frequency fs. So I should make sure that f max must be equal to fs by 2. If not, I have to use a filter to cut off the highest frequency. You should always make f max, see to that f max is equal to fs by 2. If not, you just decide accordingly by using appropriate filters. Or you can choose fs is equal to 2 times of f max, a number around to f max. Ideal choice for selecting sampling frequency is the condition. Why? Otherwise, it will lays into another signal in the range minus fs by 2 to plus fs by 2. So for a unique representation of analog signal with the maximum frequency, f max will be fs greater than or equal to 2 f max. It is to avoid aliasing. This is to avoid aliasing problem. Okay. Fs is equal to 2 f max. Is called the critical sampling rate and it is denoted by Nyquist rate. The sampling rate will be called as Nyquist rate. And I just want to ensure one thing, please understand, if you select Fs is equal to 2 f max in any of these cases, a non-shifted sinusoidal signal when sampled with Nyquist rate will produce only 0 sample sequence because of sampling at 0 crossings. When you take a non-shifted sinusoidal signal with Fs is equal to 2 into f max, the sequence of samples will be of only 0 sample sequence because the samples will be exactly selected at 0 crossings. Is it so? If so, how to avoid it? To avoid 0 crossing sampling, we must always select Fs is equal to f max. Fs must be greater than or equal to 2 into f max. Is equal to f max and the 2 into f max will be called as Nyquist rate. A non-shifted version of sinusoidal signals, when they are sampled, if the sampling rate is Nyquist rate exactly, then it will create a issue of generating only 0 samples. Okay. A discrete time signal can be reconstructed to analog signal only if it is sampled without aliasing. This is called a perfect sampling process. Perfect sampling process. Sampling theorem. One of the important statements to be remembered. Any arbitrary band limited continuous time signal with highest frequency with bandwidth f maximum hertz that can uniquely be recovered from its samples provided that Fs is selected such that it is greater than or equal to 2 into f max samples per second, provided the sampling rate is greater than or equal to 2 times of f max. Any signal, arbitrary signal xa of t, whose maximum frequency is f max, if it is to be sampled using a sampler, then the sampling frequency must be, immediately look into the maximum frequency, decides is that any value Fs which is greater than or equal to 2 into f max will produce x of n, which will be the unique representation of x of t. X of n is generated from x of t, that is called a sampling process. For sampling, I need to know what is the maximum frequency. If the maximum frequency is f max, then I have to select sampling frequency greater than or equal to 2 f max. Is that clear to you? With some more examples in the next video, numerical problems, I can definitely explain you the concepts thoroughly. So what we have seen in this short video, it is all about sampling and aliasing. Two sinusoidal signals with the frequency in the range of minus 1 by 2 to plus 1 by 2 in discrete time format are distinct. Any discrete time sinusoid with the frequency f greater than 1 by 2 will be identical to another discrete time sinusoid with the frequency range f less than 1 by 2. So range of discrete time sinusoid frequency is minus 1 by 2 to plus 1 by 2. You have to remember this. But range of analog frequencies may be minus infinity to plus infinity. That's the difference. While sampling analog signals, the infinite frequency range will be mapped into continuous, converted into finite range of discrete time signals. Small f is equal to capital F by Fs. Small f is a number between minus 0.5 to plus 0.5, but capital F will be from between minus infinity to plus infinity. By using relationships, if we develop a condition, f must be less than or equal to fs by 2, then we can easily sample it without any aliasing. We have told you and everything about what is meant by aliasing, and we have told you about folding frequency. So how to restrict ourselves before sampling? We have to look into the frequencies, maximum frequency, and the differences between two components if there are more than two components present in it, and how to set Nyquist rate. What will be the difficulty of using Nyquist rate, because it produces zero sample sequences because of sampling at zero crossings. To avoid zero crossing sampling of sine wave, we have to select fs greater than, far greater than 2 f max. F max is the maximum frequency in the analog signal. Thank you.